Good morning, dear student. In today's lecture, we will discuss the first type of reaction, that is asymmetric hydrogenation reaction, or the mechanism of asymmetric hydrogenation reaction using a chiral catalyst. Because in previous lecture we are very much familiar with this asymmetric catalysis and different types of chiral ligands and chiral complexes, metal complexes act as a catalyst in this catalytic process. So in today's lecture we discuss the mechanism of this hydrogenation reaction using chiral catalyst. So in this reaction, that is asymmetric hydrogenation reaction, we discuss the reaction, that is the asymmetric hydrogenation. Asymmetric hydrogenation. Asymmetric hydrogenation of methyl ester. Methyl ester of alpha alpha acetoaminocinamic acid. Methyl ester of alpha acetoaminocinamic acid with with a rhodium catalyst. Rhodium catalyst, which is a chiral catalyst. So if you consider what is the reaction, this is your alkene is there, C double bond O Me is there. So this is your ester functional group, and the another functional group is your NH C double bond O CS3. So this is your methyl ester of alpha acetoaminocinamic acid. It undergo hydrogenation reaction. Hydrogenation means addition of H2 in presence of catalyst to give a chiral product. So what you get here? We get carbon having NH C double bond O CS3. We get this carbon NH C double bond O CS3. Then one of the hydrogen, it is below the plane. Then here C double bond O Me is there, and here we get CS2, this phenyl. So, so formation of chiral complex with the help of chiral catalyst is known as asymmetric catalysis. So this is the hydrogenation reaction in which the alkene, there is addition of H2 in presence of catalyst to give a chiral compound. And if you find out its configuration, then if you see the priority order, the nitrogen will be first, then this carbonyl will be second, and this CH2 will be third. So it is 1 2 3. So it is S configuration. So whatever the product which is obtained, it is a S isomer. S configuration is there, and the catalyst used for this reaction is the rhodium catalyst. So let us discuss the catalyst used for this reaction. The rhodium catalyst is used. So here, this is your rhodium, which is attached to the phosphorus of phosphine, attached to again there is OMe and one. So we can write this as, so So why this complex, why this rhodium complex is considered as a chiral complex? Because whatever the ring which is attached to this phosphorus, they are in different plane. OMe is there, again the phenyl group is there, pH is there, again this phosphorus also have one phenyl, and one phenyl with OMe residue. So if you consider, it is OCS3 means your methoxy residue. So methoxyphenyl, phenyl, phosphoethane. So we can consider this part is methoxyphenyl, phenyl, phosphoethane molecule, and also it is attached to the double bond of norborane system. So they are attached. You can write here. This double bond and this double bond. And if you consider the complex having net positive charge, so this is a rhodium complex. It is a chiral complex because if you see the difference, these rings, that is phenyl group is here is above the plane, here it is below the plane, here it is below the plane, here it is above the plane. So they are not in same plane. And the other ligands, that is norborane is also attached to this rhodium, and if you count the electron, then it is a 16 electron species. 16 electron species. So this norborane double bond contribute 2 electrons, this contribute 2 electrons, so total 4. Again this phosphine is also contribute 2 electrons, so 4 4, 2 2 4 and 2 2 4, so total 8. And the rhodium contribute 9 electrons, so 9 plus 8 total 17, but the net charge is positive, so it becomes 16 electrons. So with the help of catalyst we can convert the alkenes, that is carbon carbon double bond, into a chiral complex, which is we already discussed. If you see this catalyst, it having an industrial application of asymmetric for the manufacturing of L-dopa. So this catalyst, it having an industrial application. It is used for formation of L-dopa. So let us discuss the mechanism of hydrogenation reaction with the help of this catalyst. So for our convenient, we can write the rhodium complex is like this. So here this is your double bond, this is your C double bond O, Me is there, this is your NH, C double bond O, CS3 is there. Okay, so for our convenient we can write R, capital R, which is equal to CO2 Me. So whatever the group is there, C double bond OMe, we denote only R. Then whatever the group, that is NH C double bond CS3, we denoted it as only a half circle with oxygen. So whatever the NH C double bond CS3 group is there, we denote half circle with a circle, a small circle, or we can consider with, it is not an oxygen, so it is a curve with a circle, so it is denoted as NH C double bond CS3 group is there. So the complex becomes, so our complex becomes double bond is there, okay, which is attached to the R group, means this group, and which is attached to the oxygen. which is attached to the oxygen, or we can write this as this group, it is attached to the oxygen. So we can write this as it is attached to the whatever the group is there. So we can write this as NHC double bond CH3 group is there. So it is denoted by a circle. So we can write this as, so whatever the group, and this is your H and this is your phenyl is there. So this complex is look like this. For our convenient, we reduce this complex into this simplest form, that is R group is for CO2Me and NHC double bond CH3 group for this oxygen, not oxygen, it is denoted by a circle. And whatever the complex we denoted it as the catalyst rhodium. So this is your phosphine, so they are bridge, and the star is indicate it is asymmetric. And again we can write this as this rhodium, which is attached to norborine of carbon carbon double bond, it is also attached to the carbon carbon double bond having positive charge. So this is our complex. So if you consider this group is above the plane, this group is below the plane, so we can write this as, one second, this is your phosphorus, this is your phosphorus star. So whatever the rhodium complex we see earlier, it is reduced to this form for our convenient. So let us discuss the mechanism of this reaction. So in the first step, if you see the first step, this rhodium complex, that is the double bond of this norborane, we can write this as here phosphorus is there, okay, is having positive charge. So this is your chiral catalyst, it will react with your substrate. So what is your substrate? The substrate, it will react with your substrate, that is double bond, R group is there, and the curve having a circle, so it will react. So what is going on in the first step, the catalyst react with the substrate to give two distereogenic intermediate. In both this intermediate, the oxygen atom of carbonyl group of acetamide functionality occupy a ligand site and coordinate to the rhodium center. In other words, we can say that this substrate act as a chelating ligands by coordination through olefinic double bond and the oxygen atom. So what is going on in the first step, if you see this complex and this substrate, so this substrate contain carbon carbon double bond and this circle. So this circle, it both are forms, or we can write this as it is not a circle, it is an oxygen, because NHC double bond CH3 is there. So I will make a mistake here, whatever the circle I will told, it is not circle, it is an oxygen, because NHC double bond CH3 and this is your oxygen. So both oxygen and carbon carbon double bond, it will act as a chelating agent, it is act as a ligand, and it will replace the carbon carbon double bond of this norborane system, and we get two diastereomers. That is, so what you get here, it will interact, because this oxygen and this carbon carbon double bond interact with rhodium, and there is a formation of two diastereomers. So what you get here, rhodium This is your phosphorus. Here the double bond having R group. So one of the double bond is replaced by the alkene, substrate alkene, and the second it is replaced by the oxygen. It is replaced by the oxygen. So we get this substrate A molecule. We consider this as A molecule having positive charge, and another molecule we get. So what you get here? Rhodium is there. This phosphorus. This phosphorus is there. Here double bond R is there, and here this is your oxygen which is attached to this double bond having positive charge. So we get a two stereoisomers. So we get two stereoisomers. So initially the complex it will interact with your substrate, both this carbon carbon double bond and whatever the oxygen of this amide group interact with this complex, and there is a formation of two diastereomers. Okay, if you consider the carbon carbon coordination to the metal center can take place through two different phases, so called Re phase and Si phase, to give diastereomers. So you are very much familiar with this Re phase and Si phase, and therefore we get two different product. If you see this, this is the mirror image of this. So this is the mirror image of this. So they are not enantiomer because this phosphine, whatever the phosphine ligand is there and whatever the ring is there, they are not in the same plane. They are in different plane. Therefore, they are considered as a diastereomers. They are not considered as a enantiomer. In the second step, the oxidative addition of dihydrogen to both the diastereomers to gives the intermediate C and D. So this complex, so whatever the complex which is formed, this diastereomers is formed, it undergo hydrogenation reaction, oxidative addition of dihydrogen to gives the next intermediate, that is C and D. So we are very much familiar with this oxidative addition. So we can write this as, so this is your rhodium, this is your hydrogen, this is your hydrogen is there, this is your phosphorus is there, phosphorus is there. Okay, this is your double bond is there having R group, and then whatever the oxygen, it also forms the bond with this. So we get this after oxidative addition. Oxidative addition, we get this isomer, that is C isomer, and similarly here also we get another isomer. H is there, double bond R is there, whatever the oxygen, it is also bind with this. This is your phosphorus, this is your phosphorus, the hydrogen is there. So this is the second step. In the first step, whatever the substrate molecule, it will binds with your chiral complex, chiral catalyst. After that, the stereoisomers A and B, it will undergo oxidative addition reaction with dihydrogen to gives C and D. As this complex also having a positive charge, this complex also having a positive charge. So the second step is oxidative addition. In the next step, there is an insertion. So insertion of these alkenes to a rhodium hydrogen bond produces another diastereomers E and F. So these complexes, they undergo insertion reaction. Insertion reaction. So in this case, there is a 1,2 insertion reaction. So in this case, they undergo insertion reaction. These two stereoisomers C and D undergo insertion reaction. So during insertion reaction, whatever the hepticity of this double bond, it is decreases by 1 unit. So in this case, both the carbons are attached to this rhodium. After insertion reaction, only one carbon is attached to this rhodium. So heptacity 2 is converted into heptacity 1. Heptacity 2 is converted into heptacity 1, and we get a complex. So we can write here, we get a complex, that is rhodium. Before that, after insertion reaction, so whatever the hydrogen, it is shift from this rhodium center to this carbon carbon double bond, and whatever the vacancy is generated after hydride shifting, this vacancy is occupied by this oxygen atom which is attached to this carbon. So we can write the structure, that is rhodium, this is your hydrogen, and this is your phosphine ligand is there, this is your carbon. Okay, it having R group is there, it having another group is there, because the heptacity is what change, and whatever the vacant site is generated here, it is occupied by the oxygen. So this oxygen, and whatever here, the position of oxygen, it is replaced by the solvent molecule. So you should remember, this step is very important. So in this case, after insertion reaction, whatever the vacancy is generated after hydride shifting, this position is occupied by the oxygen which is already bonded to this rhodium, and whatever the vacancy which is created after this oxygen changes its position, it is occupied by the solvent molecule. Again, this complex having positive charge. Similarly, here we get another complex is there, same complex is there, so we can consider this as E isomers, and the another is F isomers is there. So in this case, we get here a R group is there, this is another group is there, that is your CH2 pH, and this oxygen, it is attached, then there is a hydrogen is there, and this is your phosphorus, so they interact with each other, and the position of oxygen, it is occupied by the solvent molecule. So you should remember, this is your F isomers. So whatever the position of oxygen, it is occupied by the solvent molecule, and the shifting of hydride results into the vacancy which is filled by the oxygen which is attached to this carbon. And finally, this complex, whatever the complex which is formed, E and F, it undergo, we can say that it undergo reductive elimination reaction to gives your final product. So we are very much interested in the product, and whatever the complex which is formed, we are not very much interested in that case. So we get a product, that is R C, which is attached to this oxygen, one of the hydrogen is there, and this is your R group is there. So whatever the group is there, it is nothing but your CH2 pH group is there, CH2 pH group is there. So this is your chiral carbon. So we get this product, so we are very much interested into the formation of this product. So this complex undergo reductive elimination reaction, and we get a chiral complex which is attached to 4 different substituent, and we get the product, that is the hydrogenation of this carbon carbon double bond. Again, so this is all about the hydrogenation reaction of this carbon carbon double bond using the chiral catalyst of rhodium. So for our convenient, we reduce the larger complex into simplest form. So you should remember whatever the product which is formed, and you have to revise all this mechanism by more and more times. So thank you so much. In next lecture, we will discuss another type of reaction using this asymmetric catalysis. Okay, thank you.